Good day everyone, and welcome to where we are putting together solutions to those math and science problems that students are getting. In this video, we'll be looking at CSEC Mathematics, and specifically the topic of geometric construction. We'll be looking at the past paper solutions for the years May 2014 until 2018. Feel free to like the video and add any comments down below so we can help create other videos for you in any other areas that you are getting problems with. Don't forget to look at the description down below to follow the outline that we have given for the entire CSEC Maths syllabus. The order we suggest that you look at all the videos to cover the entire syllabus. Let's look at the 10 major topics in CSEC Mathematics, and this video looks at topic number 8, Geometry and Trigonometry. This topic is tested for 8 questions out of the 60 in the multiple choice paper 1 and for 2 full questions with 20 marks out of 100 in paper 2. This topic can be subdivided into 2 parts, into geometry or trigonometry. In this video, we are looking at geometry, and that itself can be subdivided into 4 smaller parts, into geometric construction, unknown angles or parallel lines, circle geometry, which is what this video is about, and transformation. When we looked at the past paper questions for this period, this 5-year period, the questions came 4 times in this period. Let's look at an overview of circle geometry, and there are some basic theorems that we are expected to know. So let's look at the first diagram. In that diagram, we have the 1, 2, 3, 4-sided shape, which is normally known as a dot, and it is formed from the dotted line, from the chord. So from the ends of the chord, we can see that they form an angle at the center and they form an angle at the circumference. And there's a relationship between the two of them. The angle subtended by a chord or made by a chord at the center is twice the angle subtended at the circumference. So if we have x at the circumference, then it's 2x at the center. Now notice one is inside the quadrilateral, inside the shape, and one is outside the shape, the angles. Now, if we take that and we open the legs out even further until it's a straight line, then it moves from being a quadrilateral into a 3-sided shape, a triangle. And the base will be the diameter. So now, if that's given us a straight line, that means 2x is equal to 180 degrees, and therefore x, the angle of the circumference, will be half of that, which is 90 degrees. So what does that tell us? It tells us that if we have a diameter and we form a triangle from it, where of course all 3 vertices are touching the circumference, then this is always a right angle triangle. So it is developed from the dart rule. And if we open the legs even further, then it will go back to being, well, it will continue being, 2x at the center and x at the circumference. And of course, one angle will be inside the shape and one angle will be outside the shape. Let's look at the 4th diagram. There we can see we have a radius and it's touching a tangent. And what can we see? The tangent to a circle always forms a right angle, which is a 90-degree angle, with the radius. And in our 5th diagram, another radius, and we can see there it is cutting a chord in half, means that it is bisecting it. So when a radius of a circle bisects a chord, the 2 lines form a perpendicular, meaning they form a 90-degree angle between them. And if we go to the next diagram, we see a shape which has 1, 2, 3, 4 sides. So it's a quadrilateral. And all 4 corners lie on the circumference. So it's a special type of quadrilateral. It's called a cyclic quadrilateral. And what relationship can we find within all cyclic quadrilaterals? The opposite angles in a cyclic quadrilateral are supplementary, which means that they will add up to 180 degrees. And if we have two pairs of opposite angles, then we will get 180 plus 180, which will give us 360 degrees, which follows the rules of a quadrilateral as we total interior angles. We can also see that if we extend any one of the sides, then the exterior angle, which is formed by the outside of the cyclic quadrilateral and the side that was extended, is equal to the opposite interior angle. Now let's go to the seventh diagram. And from a chord again, we can see that the chord forms an angle on the circumference in two different places. And what is the relationship between them? The angle subtended by a chord is the same anywhere in that segment, in that part of the circle. In our next diagram, we have a triangle in which all three corners touch the circumference. And if we consider that there's a tangent which meets the circle at one of the corners, then there's a relationship in which we can say the exterior angle between a tangent to a circle and the triangle is equal to the opposite interior angle of the triangle. And in our final rule, we see that we have from a point, it forms two tangents. And we have the radius on both sides, two of them. And of course, from the rule earlier on, the fourth one, we know the angle between the radius and a tangent is 90 degrees. And we have two of those occurring. So we can see in a situation like this that the tangents, the two of them formed from a point outside the circle, forms a quadrilateral that observes the same rules as a cyclic quadrilateral, which is that the opposite angles are supplementary. So they add up to 180 degrees. And let's look at the general steps that we should follow when we're solving this question. The first being that when you're doing a question, if students are getting problems, then they should make a sketch of these 8 theorems. And then identify which shape is relevant for what is being asked in the question. Redraw that shape, and then apply our rules and solve. May 2014, number 10A. The diagram below, not drawn to scale, shows a circle center O. The line BC is a tangent to the circle at B. Angle CBD is equal to 42 degrees. And angle OBE is equal to 20 degrees. Calculate, giving a reason for each step of your answer, the measure of part 1, angle BOE. Let's first of all identify that BOE and extract that triangle. And if we recall BOE, that BO is a radius and OE is a radius. So we have two radii or two equal sides in that triangle. So that is an isosceles triangle. And the interior angles of a triangle are supplementary, meaning that they will add up to 180 degrees. So if we substitute, we got 20 degrees for angle OBE, which is given. Angle OEB, the angle at E, is also 20 degrees because we know isosceles triangles have two same angles. And BOE we have to find, and that will be equal to 180 degrees. So let's solve. 20 and 20 is 40 degrees plus BOE is equal to 180. And if we want to get rid of the 40 degrees, so we are left with BOE alone on the left-hand side, the BOE is equal to 180 minus 40. As such, angle BOE is equal to 140 degrees. So we've solved for part 1 of the question. May 2014, number 10A, part 2. Calculate angle OED. Now, if you look at that small angle there, it's actually a part of a larger angle BED. So let's see if we could deal with that first. What do we know? Let's extract it. And it looks like our 8th rule on the right side. And the theorem states that the angle subtended by a tangent and a triangle, and we can see that there, the tangent and the triangle, which is 42 degrees, is equal to the opposite interior angle. So, angle BED, it's the same as angle CBD, the angle on the outside by the tangent. Thus, angle BED is equal to 42 degrees. And now, since we know that large angle there, let's extract it. And in green, we know that's 42. And we know 20 degrees. That's the smaller angle. Because from part 1, we could recognize that small triangle OBE is an isosceles triangle. So, angle BEO plus angle OED, the angles we have in red, would be equal to the angle in green, angle BED. Let's substitute 20 degrees plus angle OED is equal to 42 degrees. If we want to find angle OED, let's carry the 20 across. You'll get 42 minus 20. As such, angle OED is equal to 22 degrees. So, we've solved part 2 of the question. May 2014, number 10A, part 3. Calculate, giving a reason for each step of your answer, part 3. Angle BFE. Now let's recall from part 1 that we worked out angle BOE to be 140 degrees, which was the inside or minor angle. As we extracted there, we can see it in purple coming up. And what does that tell us about the outside or major angle, which we have in red? Well, angle BOE, the major angle, the one on the outside, would be 360 degrees minus 140. Because the two things add up to 360, a whole circle. So if we substitute, we'll get 360 degrees minus 140 degrees, because that's what we got before, part 1. And that gives us 220 degrees. So now that we know that, let's extract that part, and we can see this theorem, the angle subtended by a chord at the center, is twice the angle subtended at the circumference, because this comes from the 3rd rule. So if we know that, then we can say angle BFE, which is the one at the circumference, will be half of the major angle. So it will be 220 degrees divided by 2, which is 110 degrees. As such, you've solved the part 3 of the question. May 2016, number 10A, part 1. The diagram below, not drawn to scale, shows a circle, center O. EH and EF are tangents to the circle, meaning those two lines touch the circle at one point each. FOG and JOH are straight lines. They're passing through the center, which means that they are both diameters. The measure of angle FEH is equal to 44 degrees, which is given in the diagram. Calculate, giving reasons for your answer, the measure of angle EHF. So, if we look at where EHF is, it deals with that triangle on the outside of the circle. So let's extract it. And if we extract it, we can see that it looks like that last rule on the right hand side. And what does that tell us? The theorem says the tangents to a circle from an external point are the same length. So what does that tell us about the triangle EFH? It tells us that two of the sides are the same, meaning it's an isosceles triangle. So let's recall that if we add up all three angles in an isosceles triangle, it will give us 180 degrees. And two of those angles, the angles EFH and angle EHF, are the same. So you can say 2 EHF plus 44 degrees is equal to 180. So if you want to get rid of the 44 from the left side, it's adding when carried across, it will subtract. So we'll get 2 EHF is equal to 180 minus 44. And we can work that out, and that'll give us 136 degrees. So if you want to find EHF, then we have to divide by 2. So 136 over 2, and that will give us 68 degrees. So 68 degrees is the angle that they're asking us for in part 1. May 2016, number 10A, part 2. Calculate, giving reasons for your answer, the measure of angle FGH. And let's extract that, because if we look at that there, we can see we have a tangent to a circle, which looks like the rule number 8 on the right hand side. And the theorem states that the angle subtended by a tangent and the exterior angle of a triangle, that's the angle in black, is equal to the opposite interior angle, the angle we have in red. So let's recall from part 1, EHF of 68 degrees. So angle FGH, it's the same as angle EHF, which is 68 degrees. May 2016, number 10A, part 3. Calculate, giving reasons for your answer, the measure of angle JHE. So if we take a look at the diagram, and we look at where JHE is, that consists of two lines. So let's extract that. And does that look like any of the rules on the right hand side? Well, it deals with a circle and the tangent. So it looks like the fourth rule on the right hand side. And what can we tell? The theorem states the angle subtended by a tangent and the diameter is a right angle. So JHE is equal to 90 degrees. May 2016, number 10A, part 4, the last part of the question. Calculate, giving reasons for your answer, the measure of angle JGH. So let's take a look at JGH, and you can see that forms a triangle. And let's see if we can extract that. And what does that look like? It looks like the second rule. And the theorem states that the angle subtended at the center, which in this case is a straight line, 180 degrees, is twice that at the circumference, which is 90 degrees. So angle JGH, the one at the circumference, would be angle JOH divided by 2, which is 180 degrees divided by 2, which is 90 degrees. As such, this angle JGH is a right angle triangle. May 2017, number 10A, part 1, P, Q, R, and S are 4 points on the circumference of the circle shown below. And if we connect the 4 points, we can see that that is called a cyclic quadrilateral. Angle QRS is equal to 58 degrees, and that's also shown. Using the geometrical properties of a circle to give reasons for each step of your answer, determine the measure of angle SPQ. So if we look at this cyclic quadrilateral, let's extract it. And it looks like the diagram 6 on the right hand side. And what's the ruling? The theorem states that the opposite angles in a cyclic quadrilateral are supplementary, meaning that if we add up the opposite angles, it will give us 180 degrees. So angle SRQ, the angle at R, and angle SPQ, the angle at P, is equal to 180 degrees. Let's substitute. 58 degrees plus angle SPQ is equal to 180. So if we want angle SPQ, we carry it across, so we get 180 degrees minus 58 degrees. So the angle is 122 degrees. This is the opposite angle in that cyclic quadrilateral. May 2017, number 10A, part 2. Using the geometrical properties of the circle, find the angle OQS. And if we look at that angle, OQS, that's within the small triangle, but we have no angles in there. So let's see if we can use the dot, the 58 degrees, to help us find an angle in this small triangle. Let's extract it. And that dot looks like the first rule on the right-hand side, which states that the angle subtended by a chord at the center, and we have that in the red arrow, is twice the angle subtended at the circumference. So, angle SOQ is equal to 2 times angle SRQ. And we know SRQ, so we can substitute. Angle SOQ is equal to 2 times 58 degrees, which is equal to 116 degrees. So we now have an angle inside of the triangle. Let's now extract that triangle. And what do we know? We know that since O is the center of the circle, OQ is a radius, OS is a radius. So we have 2 radii in this triangle, meaning that we have 2 sides that are the same. So it's an isosceles triangle. And if we have 2 sides that are the same, then we have 2 angles that are the same. The angle at S, or OSQ, is equal to the angle at Q, OQS. So let's recall that when we add up all 3 angles in a triangle, the angle at S, the one at Q, and the one at O, it will be equal to 180 degrees, and 2 of them are equal. So we can rewrite it 2 times angle OQS plus 116 degrees is equal to 180 degrees. What do we do now? We carry the 116 across, so we get 2 times angle OQS is equal to 180 minus 116, and 2 OQS is equal to 64 degrees. To find angle OQS, we now divide by 2, and that will give us 32 degrees. So angle OQS is 32 degrees. May 2018, number 10B, part 1. The diagram below, not drawn to scale, shows a circle center O. The points C and M are on the circumference. The straight line CN is a tangent to the circle at point C and is perpendicular to BN. And we can see from this diagram ABMC is a cyclic quadrilateral because it's a 4-sided shape and all 4 corners touch the circle. Triangle ABC, we can see from there that this triangle has a diameter AB because it's passing through O. So since we want to find angle ABC, let's look at that triangle. Let's extract it. And which rule does it look like? Because AB is a diameter. If we look on our right side, we have one rule with the diameter. That's the second rule. So the theorem states if it's a diameter, it means that that curve is a semicircle. So the semicircle forms a right angle triangle. If it forms a right angle triangle, then we know 2 angles in there. And all 3 angles add up to 180 degrees. Angle A plus angle C plus angle B is equal to 180 degrees. Let's substitute. 58 degrees plus 90 degrees plus angle B is equal to 180. That means 140 degrees plus angle B is equal to 180. If you want angle B, it would be 180 degrees minus 148 degrees. So angle B is equal to 32 degrees. Therefore, angle ABC, which is what we wanted to find, is 32 degrees. May 2018, number 10B, part 2. Determine, giving a reason for your answer, angle CMB. And if we look at that angle, it's part of a triangle and it's also part of a cyclic quadrilateral. So let's see which rule we can use. What does that look like? Dealing with cyclic quadrilaterals, it's the 6th rule on the right-hand side. And the theorem states that the opposite angles in a cyclic quadrilateral are supplementary. What does that mean? It means it adds up to 180 degrees. So if we add the angle at A, which we know, and the angle at M, which we want to find out, it should give us 180 degrees. So let's write that angle CAM plus angle CMB is equal to 180 degrees. And we can substitute 58 degrees plus angle CMB is equal to 180 degrees. If we want angle CMB alone, carry the 58 across, it will be 180 minus 58, which is equal to 122 degrees. As such, we found the angle that was required. May 2018, number 10B, part 3. Determine, given a reason for your answer, angle NCM. So if we look at angle NCM, it forms that part of that small triangle, which is a right angle triangle. So if we were able to find out the angle at M, then we can substitute, because we know there's a right angle in there. We have two of the angles, we can find the one that's required. So let's see if we can find that angle at M. Let's extract that straight line, that NMB line. And what do we remember? Remember that when we have a straight line, the angles involved are supplementary. So the angle on the left side of it, or on the lower side of it, plus the angle above will be equal to 180 degrees. Angle CMB plus angle CMN is equal to 180 degrees. And we can substitute 122 degrees plus angle CMN is equal to 180 degrees. So angle CMN is equal to 180 minus 122 degrees. So angle CMN is equal to 58 degrees. Now we have an angle within the triangle. So we have two angles actually. So let's extract that triangle. Look, it's a right angle triangle. We have two angles. So we can find angle NCM, the one that's missing. So angle CMN, which we just got, plus angle MNC, which is a right angle, plus angle NCM, which we want to find, is equal to 180 degrees. Let's substitute 58 degrees plus 90 degrees plus NCM is equal to 180. So 148 degrees plus angle NCM is equal to 180 degrees. And angle NCM will be 180 degrees minus 148 degrees, which is 32 degrees. So angle NCM is 32 degrees. We've now come to the end of CSEC past paper questions in the topic of circle geometry. In our last video, we completed past paper questions from 2009 until 2013, and in this video, we looked at the next 5 years from 2014 until 2018. Our next video will carry us from 2019 until the present. Don't forget to look at the description down below to get an overview of the entire CSEC Maths syllabus.